Hello, class. It's nice to meet you once again. So today we'll be looking at the different forms of carbon. There are different forms of the element carbon. We'll be considering two crystalline forms of carbon in this class, which are diamond and graphite. When elements behave in this manner, where they appear in two or more different physical forms, we call this phenomenon allotropy. Okay, that phenomenon is called allotropy. Okay, when you have a particular element exhibiting two or more forms in the same physical state. So diamond is one form of carbon. I know you must have been familiar with carbon being a dark, substance. But that carbon exists in different forms. So we'll be considering just two of those crystalline forms today. We also have the amorphous forms of carbon, but today we'll be sticking to the crystalline forms only. Diamond is one of the crystalline forms of carbon. Okay, is known for its hardness, which is due to the covalent bond in the giant lattice structure that it has. Okay, this can be thought as a continuous network of atoms linked by covalent bonds. Okay, so these covalent bonds, if you would recall when we treated bonding, covalent bond is a strong bond. Okay, so this is the only type of bond that exists in the structure of diamond. So if you examine the structure closely, you will see that each of the carbon atom is covalently bonded to four other carbon atoms. Let me show you that in this structure. Let's just pick one carbon as an example. Let's pick this one. Okay, as you can see in this structure, this carbon that I encircled here is bonded to another carbon at the top, another carbon below, another carbon by the right, and then another one by the left. Okay, so if you keep on picking each of these carbon atoms, they are all bonded in the same manner. Okay, so each carbon atom bonded to four different carbon atoms, covalently. Okay, so that makes this arrangement for diamond a very strong one. Okay, and that is what is responsible for the hardness of diamond, as shown in the diagram above. So we move on to graphite. Okay, so graphite, on the other hand, is another form of carbon, though unlike diamond, diamond is transparent, looks like glass, like broken glass, and has this high refractive index that can refract colors of your white light. So that makes diamond unique. Okay, and that refraction is due to the fact that diamond has a very high refractive index, so it can refract your white light, when seen. But graphite, on the other hand, is opaque. Is opaque. Okay, is opaque, so you can't. It does not have those properties that diamond has, but it also have this giant covalent structure. But unlike diamond, each of these is bonded to other three layers, not four. And then you have the layers, held together by weak forces of attraction, which we generally call molecular bonds, okay, intermolecular bonds. Okay, these bonds are weak. So what happens when covalent compounds are held by weak intermolecular bonds? In the last class, we said it makes them have this low melting, low boiling point, and makes them appear weak. Okay. For graphite, due to this arrangement, because it's arranged in sheets. Okay. It's arranged in sheets that are held by this, you can see different sheets, denoted by the dotted lines. And if you hold one carbon here, you would notice that each carbon is joined by other 3 atoms, not 4, unlike diamond that's bonded 4. For graphite, we have just 3. Okay, we have just 3. And that gave room for the presence of electron. Okay, so there are delocalized electrons. Why do we say they are delocalized electrons? Okay, let me quickly show you that. Carbon on your periodic table has atomic number 6, which denotes it has 6 electrons. So the outer shell, the inner shell will take 2, the outer shell will take 4, which denotes that carbon has 4 outer shell electrons. Okay, so if it has 4 outer shell electrons, it is expected that carbon should bond to 4 different atoms. But when for graphite, when you have just 3 carbon bonded to it, to each atom, you have this free one here. For diamond, the bonding is 4 completely, so there's no free electrons. But for graphite, there is 1 free electron on each carbon atom. So this free electron is mobile. So as these electrons are free, you know what it denotes when it comes to conduction of electricity. For a material to conduct electricity, there must be presence of delocalized electrons. Okay, so that makes graphite a good conductor of electricity due to this arrangement. Now, due to the fact that the sheets are held by weak forces, the structure of graphite can slide, each layer can slide over each other. That is what is responsible for its softness and its use as lubricant in high temperature machine. Okay, so this is a good place to end the class. As you can see, the comparison of the physical properties of diamond and graphite shown on the table. Of course, diamond is stronger based on what we've discussed so far. Diamond has a very high melting point of 3,500. Okay, graphite too, of course, due to the covalent bonds, also have a high melting point. The hardness, on the other hand, diamond is very hard, unlike graphite. Graphite is soft because of the layers, that are not bonded together, and so can slide easily over past each other. And then conductivity, of course, diamond does not have any free electrons, so it does not conduct electricity. But graphite has delocalized electrons, okay, that's free to move, and they conduct electricity. In fact, graphite is the only non-metal that conducts electricity very well. Okay. So diamond is used to make your jewelries, used to making drilling bits due to its hardness. Okay. Graphite, on the other hand, used in making your pencils because it's soft, you can rub on paper, and used in making electrodes because it's a good conductor of electricity. So we'll stop the class here today. We'll continue some other time. So thank you for listening. Don't forget to hit the subscribe button, subscribe so that you can always be up to date with more videos that will be coming your way. So at the juncture, I would like to say bye till we meet again.